Welcome students. You have been introduced to the lattice structure and type of bonding in crystalline solid in my earlier lecture. You know that the behavior of electrons determine the way of the atom interact, the type of bonding like metallic, ionic, covalent and van der Waals that hold atoms in a solid together. But is the knowledge of bonding and crystal structure sufficient to predict the microscopic property of materials? In this lecture, we will discuss different types of imperfections or defects in the ideal arrangement of atom in a crystal. Real crystals are never perfect. There are always defects. Crystals are like people. It is the defect in them which tend to make them interesting. This is a quoting by Colin Humphrey. We will see that the presence of a relatively small number of defects have a profound impact on the macroscopic properties of materials, and the control of defects is very important in many kinds of material processing. For example, when you buy a diamond ring, it is mostly the number and type of defects in the diamond crystal that defines the amount of money you have to pay for a given crystal size. So, the relevance of defects in crystal for the life in general or material science in particular is of great importance. In general, there are lots of properties that are controlled or affected by defects. For example, electric and thermal conductivity in metals, electronic conductivity in semiconductors, diffusion, ionic conductivity, plastic deformation in crystalline material, colors and mechanical strength. Coming to the definition, any deviation from the perfect ordered arrangement of the constituent particle in a crystal is called imperfection or defect. Crystal defects are broadly classified into three types, namely point defects, line defects and plane defects. First, point defects. They are the irregularities or deviation from the ideal arrangement around a point or an atom in a crystal, whereas the line defect are the irregularities or deviation from ideal arrangement in entire row of lattice points. Line defects affect the mechanical properties of a crystal and cause its easy deformation under the influence of a shear stress. Plane defect. It is the disruption to the periodic arrangement of lattice points along a plane. Therefore, the plane defect affects the mechanical properties of a crystal and also its chemical reactivity. Today, we shall confine our discussion to the point defects only. Point defects can be classified into three types: stoichiometric defects, non-stoichiometric defects and impurity defects. Let us first discuss the stoichiometric defects and its classification. These are the point defects that do not disturb the stoichiometry of the solid. That is, the ratio between the cations and anions remains the same as represented by their molecular formula. They are also called intrinsic defects or thermodynamic defects. The stoichiometric defects are of two types: vacancy defects and interstitial defects. First, vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in decrease in density of the substance. Interstitial defect. When some of the constituent particles, atoms, molecules or ions occupy the vacant space in the crystal lattice known as interstitial site, the crystal is said to have interstitial defect. The particles present in the vacant space are known as interstitials. This defect increases the density of the substance. Vacancy and interstitial defects, as explained above, can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality. Rather than simple vacancy or interstitial defects, they show these defects as Frankel and Schottky defects. For an ionic crystal, the ratio of the number of constituent positive and negative ions remains the same, just as indicated by its chemical formula, even in the absence of such defects. Next, we will see the Schottky defect. The Schottky defect or small shot effect is named after a popular German physicist, Walter S. Schottky, who has even awarded the Royal Society's Hughes Medal in 1936 for the discovery of this effect. In his model, he explains that the defect is formed in ionic crystal when oppositely charged ions, cation and anion, leave their lattice site, which lead to the creation of vacancies. Since both the cations and anion leave the lattice sites at the same time, so overall electrical neutrality of the crystal is maintained. However, density reduces because of the vacancies. Another important consequence of Schottky defect is that their presence enables the crystal to conduct electricity to a small extent by an ionic mechanism. Under the influence of an electric field, an ion migrates into a neighboring vacancy. This creates a new vacancy into which another ion can migrate. Continuation of this process, which is commonly referred to as the vacancy mechanism, result in the migration of the ions and the vacancies across the lattice in opposite direction, thereby causing a small ionic conductivity in the solid. A few examples of ionic compounds exhibiting Schottky defects are NaCl, KCl, AgBr, CaCl, etc. To summarize the characteristics of Schottky defect, this defect occurs only when there is very small difference in size between cation and anion. Cation and anions both leave the solid crystal. Here, atom also move out of the crystal permanently. It maintains the electrical neutrality of the crystal. Mass decreases while volume remains the same. And finally, as for the density of the solid, it decreases considerably. Okay, let's see what is Frenkel defect. Frenkel defect is another form of a point defect which is created when an atom or cation leaves its original place in the lattice structure to create a vacancy while occupying another interstitial position within the solid crystal. This defect creates vacancy defect at original site and interstitial defect at new site. So, we can say this defect is a combination of vacancy defect and interstitial defect. The Frenkel defect is also called a dislocation defect. Do you know the examples? Yes, AgBr, ZnS, AgCl, AgI, etc. are the ionic compounds which show this crystal defect. The characteristics of Frenkel defects are: these defects are common in ionic compounds which have larger difference in size between cations and anions. Since no ions are missing from the crystal as a whole, Frenkel defect do not affect the density of the solid, and therefore, both the volume and mass of the solid is preserved. Their presence does not affect the electrical neutrality of the crystal. There is an increase in the dielectric constant as the light charged ions comes closer. The solids having Frenkel defect show conductivity and diffusion in solid state due to the presence of vacant lattice sites. Due to Frenkel defect, the lattice energy and stability of the crystalline solid decreases and influences the chemical properties of ionic compounds. Now, let us see the second type of point defect, non-stoichiometric defects. The defect which disturb the stoichiometry of the compound are called non-stoichiometric defects. These defects are either due to the presence of excess metal ions or excess non-metal ions. Here, the electrical neutrality is maintained by the accommodation of free electrons or extra positive charges. There are two main types of non-stoichiometric defects. One, metal excess defect, and second, metal deficiency defect. So, first, metal excess defect, or we can say non-metal deficiency defects. Imperfections caused by the presence of excess metal ions, then what is required to maintain the stoichiometric composition of the compound are called metal excess defects. These can arise in two different ways. One, due to extra interstitial cations, and the other due to anion vacancies. Sometimes an extra cation may be trapped in an interstitial site of the crystal. Here, the electrical neutrality is maintained by the presence of sufficient number of electrons in other interstitial sites. Such a defect constitutes a metal excess defect due to extra interstitial cation. Example, when sedano is heated, it reversibly loses oxygen and turns yellow in color due to the formation of non-stoichiometric zinc oxide containing metal excess defects. The excess Zn2 plus ions are trapped in interstitial sites. Free electrons are also trapped in neighboring interstitial sites to maintain electrical neutrality. These free electrons absorb light to undergo transition to a higher level and are responsible for the yellow color. Sometimes anion vacant lattice sites in a crystal may be occupied by electrons, thereby maintaining electrical neutrality, but causing a metal excess situation. Such an imperfection constitutes a metal excess defect due to an anion vacancy. Example, when a sodium chloride crystal is heated in sodium vapor, it acquires a yellow color due to the formation of non-stoichiometric sodium chloride. Here, sodium metal gets doped into the NaCl crystal. The sodium atom gets associated with the lattice and settle in normal cation site, creating an equivalent number of anion vacancy in the crystal. These sodium atoms subsequently ionize into Na plus ion and electrons. The released electrons occupy the anion vacancies. These free electrons, which are capable of absorbing light, impart yellow color to the compound. The lattice site in which an electron is trapped is called F center or color center. The F comes from the German word Farb, which means color. This is because such an electron has a delocalized nature and can undergo transition to a higher level by absorbing visible light, thereby imparting color to the non-stoichiometric compound. The color produced by the F centers is always characteristics of the host crystal. For example, sodium chloride, yellow, KCl, violet, KBr, blue-green color. Due to the presence of free electrons in lattice sites or interstitial sites, compounds containing metal excess defect show some electrical conductivity and act as N-type semiconductors. Second classification, metal deficiency defects or non-metal excess defect. Sometimes a positive ion may be missing from its lattice site, the electrical neutrality being maintained by some of the neighboring positive ions, acquiring greater positive charges. Such a defect is called a metal deficiency defect. This kind of defect generally occurs in an ionic compound of those metals which are capable of exhibiting variable valency. Example, in woodsite FeO crystals, some Fe2 plus ions are lost. For each missing Fe2 plus, two other Fe2 plus ions are converted into Fe3 plus to maintain electrical neutrality. Woodsite is thus non-stoichiometric with metal deficiency defect. The case of iron pyrite or FeS is very similar. Existence of cations in different oxidation states in the lattice provides opportunity for free electron exchange. Transfer of electron from one Fe2 plus to a nearby Fe3 plus interchanges the position of the two. Such electron transfer in one direction thus lead to the movement of Fe3 plus in the other direction, and this in turn lead to some electrical conductivity. Such movement being equivalent to positive hole migration, these compounds act as p-type semiconductors. This free electron exchange also give rise to metallic luster. Thus, some sample of iron pyrite mineral shine like gold and have been named fool's gold. Other examples for metal deficient non-stoichiometric compounds are CuS, NiO, etc. And last, we have impurity defects or eccentric defects. Sometimes positive ions are found missing from their lattice site and the electrical neutrality is maintained by the presence of some foreign positive ions. Such an imperfection is called a substitutional impurity defect. Example, suppose two silver ions are missing from the AgCl or AgBr lattice and that one of these cation vacancy is occupied by an ion of comparable size, say cadmium 2 plus, leaving still one cation vacancy in the crystal. The irregularity thus produced constitutes a substitutional impurity defect. Such substitution of lattice constituents by impurity ion often introduces semiconducting properties and color in the compounds. Eccentric defects of the substitutional impurity type are produced in semiconducting materials like silicon through the process of doping to enhance conductivity. These N-type and P-type semiconductors produced are of great importance in semiconductor industry. This topic will be discussed in the later part of this section. Extrinsic defects may rise in the crystals due to small impurity atom occupying interstitial sites, that is non-lattice sites. For example, impurity carbon atoms with a radius of 0.071 nanometer fit nicely in the interstices between the larger ion atom with radius 0.124 nanometer to produce steel. Similarly, hydrogen atoms can fit easily into the interstices between palladium atoms in the palladium crystals. Well, I think the topic related to defects are clear for everyone. Shall we move on to our next topic? Semiconductors. I have a question for you. Do you know some examples of semiconductors which are used in our day-to-day life? Most of the electronic gadgets we use are made up of different semiconductors. For example, mobile phones, laptops, television, digital camera, automobiles, washing machines, etc. So, I think it is very important for us to learn more about this topic. Coming to the definition, the solid which have conductivities between conductors and insulators ranging from 10 raised to minus 6 to 10 raised to 4 ohm inverse meter inverse are called semiconductors. Conductivity of electricity in semiconductors like silicon, germanium, etc. are based on the temperature and addition of impurity. In semiconductors, the valence band is almost full while the conduction band is mostly empty. The forbidden energy gap is quite narrow, thus the heat energy available at room temperature is sufficient to excite some of the electrons from the valence band to the conduction band, which result in the conduction of electricity to some extent. The conductivity of semiconductors increases with increase in temperature, since more electrons can jump to the conduction band. Now, let us study different types of semiconductors and how conduction of electricity takes place in semiconductors. Types of semiconductors. There are two types of semiconductors, intrinsic semiconductors and extrinsic semiconductors. The semiconductors which can conduct electricity in their pure form are called intrinsic semiconductors. At room temperature, the conductivity of these semiconductors are quite low. Example, germanium and silicon. The process of adding small amounts of impurity to an intrinsic semiconductor is known as doping, and the impurities are called dopants. Eccentric semiconductors. The semiconductors formed by adding impurity to an intrinsic semiconductor are known as eccentric semiconductor. Example, when germanium is doped with arsenic as impurity, it becomes eccentric semiconductor. Now, we know what is doping. Let us study how an intrinsic semiconductor can be doped. Doping can be done in two ways, with electron rich impurities or with electron deficiency impurity. First, electron rich impurities. Both silicon and germanium belonging to the group 14 of the periodic table and have 4 valence electron each. When silicon is doped with small amount of group 15 elements such as phosphorus, arsenic, the electrical conductivity increases. In pure silicon, each silicon atom uses its 4 valence electron for the formation of 4 covalent bonds with neighboring silicon atoms. When silicon is doped with some group 15 elements, then some of the positions in the lattice are substituted by the atom of group 15 element. The group 15 elements have 5 valence electrons. After forming the 4 covalent bonds with silicon, one excess electron is left on them. Since this electron is not involved in bonding, it becomes delocalized and contribute to the electrical conduction. Silicon doped with the group 15 elements is called N-type semiconductors. The increase in conductivity is due to negatively charged electrons. So, semiconductors doped with electron-rich impurity are called N-type semiconductors. Electron deficient impurities. Electrical conductivity of silicon or germanium can also be increased by doping with group 13 elements such as boron, aluminum and gallium. When silicon is doped with some group 13 elements, some of the positions in the lattice are substituted by the atoms of group 13 elements. Group 13 elements have only 3 valence electrons. Thus, they form only 3 covalent bonds with 3 silicon. One of the valence electrons of the silicon remain unpaired. This causes an electron vacancy or electron hole in the system. To fill this vacancy, an electron from the neighboring atom jumps to the electron hole, creating an electron hole at its original position. When the electric field is applied, electrons migrate towards the positive electrode by filling the holes, making it appear as if electron holes are migrating towards the negative electrode. These holes are responsible for electrical conduction, and the resultant semiconductors are known as p-type semiconductors. Let us see the effect of temperature on electrical conductivity. Electrical conductivity of metals decreases with increase of temperature, whereas the conductivity of semiconductors increases with increase in temperature. Why? In metallic crystal, the electrons are free to move throughout the crystal. However, the metal ions are fixed in positions and can only vibrate. When the metal is heated, the metal ions start vibrating more vigorously, and as a result, the motion of valence electrons through the crystal is hindered. Thus, electrical conductivity of metals decreases with increase in temperature. In semiconductors, the energy gap is very small. A slight increase in temperature or application of small voltage, some electrons from the valence band jump to the conduction band and show low conductivity. Substances exhibiting this type of behavior are known as intrinsic semiconductors. Example, silicon, germanium, etc. So, with this I am concluding this session. Today, we have discussed the different types of defects or imperfections in crystal structure, semiconductors and its importance. Hope the session is clear for you. Thank you.